Welcome to Math 31. This is lesson 9 on the applications of trig functions. Now, I'm only scratching the surface with the applications. You will find that there's, as you're in your journey through calculus, that you'll have lots and lots of applications that I'm not looking at. But the basic idea tends to be the same. And most of what you learn in this section are, most of the skills are fully transferable to a number of other trigonometric type applications. And usually the applications you work with will involve an angle, which makes sense because that's the nature of trigonometry. The very first one I look at, actually not so much, but is still useful in its own regard. It's kind of an unusual question. So in this case, this takes us back to the old motion problems that we dealt with early on in applications. We've got a particle moving along a straight path, but it's got a very funky type of position function because it's a trigonometric one. S of t is equal to t sine pi t, where s is in meters. Question is, we want to find the velocity and acceleration when t is equal to 3 over 2 seconds. Now, this in itself isn't that difficult of a problem because you just need to remember that to get the velocity function, we would take the derivative of the position function. And in this case, we would have to use the product rule to break this one up. I'm not going to take it to the side and work it out. Rather, I'm just going to deal with it in front of me. It's a simple enough one. The derivative of t is just 1, and then 1 times sine of pi t. So the v stays the same, plus the t stays the same, and then the derivative of sine is cosine pi t, but we need to multiply that by the derivative of the inner, which is pi. So it turns out to be pi t cosine pi t. Now all we have to do is evaluate this at t is equal to 3 over 2. So we will get the sine of 3 over 2 pi, so 3 pi over 2. That's a familiar angle, plus 3 over 2 pi multiplied by the cos of 3 pi over 2. And when we simplify further, we will get -1, which is the sine of 3 pi over 2. And then this second part, 3 over 2 pi, looks like it's going to be a problem, but the cosine of 3 pi over 2 is 0, so problem solved. So we end up with -1 meters per second for the velocity at t is equal to 3 over 2. Now the next part, of course, is the acceleration, and that's not a big deal. We just have to keep on differentiating. So a at t is equal to the derivative of v. Now v at t, just to recap this, on the previous page we had v at t is equal to sine see if we can remember. V at t is equal to sine pi t. Okay, that's what we want. Sine pi t, and then plus pi t cos pi t. I had to think there for a second. Now, when we differentiate this, we get some good news and some bad news. A as a function of t will be equal then to the derivative of sine, which is going to be cos pi t. That doesn't involve anything like the product rule, multiplied by the derivative of the inner, which is pi. So pi cos pi t. And then when we differentiate the other one, here we do have to use the product rule. This is u, this is v. So when you're going to use the product rule in a case like this, remember the coefficients, in this case pi, keep it with the t and treat that as the u. And when you differentiate that, that is going to give you just pi. And then times the cos of pi t. And then the second part, the pi t, stays as, and then we take the derivative of cos, so we get sine of pi t. And then we differentiate the middle, and we get another pi. So it's actually pi squared. And then it's minus, because the derivative of cos is negative sine. So negative pi squared t sine pi t. And then when we get a at 3 over 2, with care, we replace this in. Now I should also, before we go on with that, these are actually like terms. Pi, cos, pi t, these could be added together. So that would give you 2 pi. And so I will indicate that when I substitute it in. You'll see it won't make a lot of difference. So 3 over 2 pi, because that one's going to be 0 anyways. And then minus pi squared times t, which is 3 over 2, multiplied by the sine of 3 pi over 2. Working our way downwards, of course, 2 pi times 0, because the cos of 3 pi over 2 is 0. And then this becomes minus pi squared times 3 over 2. And then the sine of 3 pi over 2 is again negative 1. So this turns into positive 3 pi squared over 2 is a at 3 over 2. And that would be meters per second squared. So not a great answer, but the correct one. Now the more common problems you're going to get are more conventional angle type things. So you take a look at this one. Making sense of this question is the first thing, even though you do have a diagram. What you've got is this revolving light, and it's 100 meters off the nearest point on a straight shoreline, which I'm just going to call X before we get too deep into this one. And that light is sort of panning across the shoreline from its fixed position 100 meters away from the beach. Now, this is a question that clearly requires you to use trigonometry because of the angle involved. This thing is rotating, so there's a rotation. So any regular related rate problem or method would be inadequate. You have to integrate trigonometry into it. But otherwise, it's a fairly conventional related rate. Now, as you can imagine, because of the distance increasing, as you're, say, in this case, 200 meters away from P, that the speed that the thing is moving is going to be changing. So it is a dynamic system. It does require calculus. It's not going to be a fixed rate. We're comparing two rates. We're comparing the rate that the light is turning, rotating, with the rate that the x, the distance, is changing. Now, this is 100 meters. We do know that. And that's fixed. Now, what we ultimately want is to find the rate at which a beam of the light moves. We want to know dx dt, the rate that x distance is changing with respect to t. So I like to indicate that first, and then find an equation that links what were the variables and the numbers that we have. And this is going to be tan, because tan theta would be equal to side opposite x over 100. And we can put the 100 in the equation because it is a constant value. It's not going anywhere. And then that turns into 100 tan theta is equal to x. Now, if we just wanted to know the distance at a specific angle, we would just plug in now. But we don't. We want to know the rate at which it's changing. So this means we have to differentiate. So we differentiate with respect to time, just like we always do for related rates. And in doing that, we'd get 100. And if you take a look at your formula sheet, you see the derivative of tan theta is secant squared theta. And then don't forget, because we're taking this with respect to time, we have to indicate d theta dt. And then that's equal to, on the right side, dx dt. I would pause for a second. I don't mean pause the recorder, I mean pause just to think. You see, we want dx dt, but we should see what we've got. And in fact, it's a little depressing because we don't have d theta dt, we don't know what that is, and we don't have secant squared theta. So we don't really have much to work with. So we have to go after those two variables if we have any hope of solving this, or these two values. But we can't. And the way we can solve it is because at x is equal to 200, which is what the question is all about, it means that tan theta at that point is equal to 200 over 100, or 2. Now remember, you cannot plug that x equal 200 into the original equation, because all you're going to get then is the angle when x is 200. But now that we've differentiated it and we've got it at this specific point, we can then plug in the x equal 200, at least into the tan part, because we're trying to find out what the rate of change is at that point exactly. Now, where we go after the secant? Some of you will think, well, if tan is 2, I can now find the hypotenuse, and then I can find cos of the angle, and then I can find secant. And of course you can, and it works well that way. But the fastest way is to use the identity, which is secant squared theta is equal to 1 plus tan squared theta. And because that's what we want is secant squared. Now this is a very common setup because very often you're working with tan, and because the derivative of tan is secant squared, you find yourself in this position frequently. So all we do is go 2 squared, so secant squared theta is equal to 1 plus 4 is 5. So there we go, we got that. Now we need to get d theta dt. Now this is the rate that the angle is changing as time changes. And here we note that one revolution takes place every 15 seconds. In trigonometric terms, one revolution is 2 pi rads. So we get 2 pi rads per every 15 seconds. So you can say 2 pi over 15 rads per second. And that is d theta dt. So we've got that now. So all that has to happen is we've even got it isolated, dx dt. So I'm going to get a little bit of space to work, substitute those values in, and then I'm going to get an answer. And this one we want to the nearest tenth, so I will decimalize it ultimately. So plugging into 100 secant squared theta, d theta dt is equal to dx dt. We would get 100 times 5 times 2 pi over 15 is equal to dx dt. Simplify the whole thing out. I guess you probably don't need to do this because it's going to be decimalized anyways, but it's 200 pi over 3, and 200 times pi divided by 3 will give you 209.4. So 209.4 now that's meters per second is the rate the light is moving at x equal 200 meters. So that's not a constant. At that point it's going that speed, but it wouldn't be going that speed at all points. Now let's do another one. There's actually on your handout you've got about 4, but I'm going to break this into 2 by 2. This one is kind of an oddball question, a little less useful than the previous one, if you can imagine that. And in fact, this is a sort of problem you could probably figure out without even doing any calculus, just by using simple reasoning power. However, I'm going to use it as an example for a maximum or minima question. So here we go with the whole thing. Find the measure of the angle that will maximize the perimeter of a triangle if the hypotenuse is 12 centimeters. And then we want to determine the maximum perimeter. So here's our situation. Here's our triangle. And this hypotenuse is 12. Now the way we want to set this one up is to understand first off that this is a maximum issue. So we're not doing a related rate with it. We're instead doing a find the critical numbers and then check to see whether those critical numbers represent a min or a max value. Now I would recommend that you select one angle and call it theta, and then x and y is conventional for the horizontal ones. I chose the theta at the bottom. Of course, it doesn't really matter which one you do. It really doesn't make any difference. Because if this is a right triangle, if you get one angle, you're certainly going to get the other angle as well. And then we note that what we are trying to maximize is the perimeter of this thing. So the x variable, we don't want to do it in terms of x, but using a bit of trigonometry, we can see that the cosine ratio would be equal to x over 12. So in fact, 12 times cos theta is equal to x. As well, for y, the sine of theta is equal to y over 12. So 12 sine theta is equal to y. And before we get too deep into this question, though, I'm going to take a minute to remind you that for applications, for maxima and minima questions, we should check the domain out. And this is a sort of question that if you didn't check it now, you'd certainly notice that you'd have to reject an answer later on. But anyways, theta has to be between 0. It has to be above 0, otherwise you don't have a triangle. And it has to be less than pi over 2. There's no way that you could have a triangle with dimensions larger than that. If you did, then you would reject that answer just based on the ridiculousness of it all. Now the perimeter is going to be equal to the x plus the y plus the 12. So it's going to be equal to 12 cos theta plus 12 sine theta, and then plus 12. So then if you took the derivative, and I'll write this as p prime at theta, because the variable in question is theta. It is not a related rate. We're not trying to find out how it's changing with respect to time. So it's just p prime at theta. The derivative of 12 cos is negative 12 sine theta. And the derivative of 12 sine theta is plus 12 cosine theta, and then plus 0. So reminder that it doesn't, that you don't have to go d theta dt at all, because we're not taking it with respect to a different variables. We're taking it with respect to theta. And then we go after the critical numbers. And the critical numbers, as I hope you're well aware, are found principally where p prime at theta is equal to 0. Because it's sine and cos, it's defined everywhere within that domain, 0 to pi over 2. So there's no point where we're finding out where the derivative doesn't exist. Going to get a little bit more space to work, but then I will set the 0 equal to negative 12 sine theta plus 12 cosine theta. Now you could do this now or you could do this later. I'm going to do it now. I'm going to divide every term, including the 0, by 12. So I get 0 is equal to negative sine theta plus cosine theta. Now you could solve this a number of ways. The conventional way, which I'm going to do, is bring the sine theta to the other side to make it positive, and sine theta is equal to cos theta. You could stop and think, where is the sine ratio equal to the cosine ratio? And then you get your answer right away. I'm going to kind of play dumb with it I'm going to divide both sides by cos theta and do it fully algebraically. So I get tan theta is equal to 1. And the conventional method then is to note that, well, tan is positive, it's in quadrant 1 and quadrant 3. Our reference angle, where tan is equal to 1, is pi over 4. And then, because you're in quadrant 1, it's going to be pi over 4. In quadrant 3, it's going to be 5 pi over 4. Now this one we reject. It's outside the domain. That's 225 degrees. I don't think that 225 degrees is going to fit within that right triangle. Now, having done all that, we can take our answer. That's our critical number. We don't have to do any interval analysis on it. You could to see if it's a min or a max, but we could use the second derivative test. Now, in fact, of course, it's going to be a max, but I'll do it anyways. So our first derivative is negative 12 sine theta plus 12 cosine theta. So we want p double prime at theta, and that's going to be equal to, well, the derivative of negative 12 sine theta is negative 12 cosine theta. The derivative of 12 cosine theta is 12 sine theta, but negative. So when we take the second derivative at pi over 4, we will get negative 12 times the cosine of pi over 4 minus 12 times the sine of pi over 4. And that's negative 12 times cosine pi over 4 is root 2 over 2, and then minus 12 times root 2 over 2. This is going to be negative. Two negative numbers being subtracted like that. You can check it out, but it's less than 0. So negative, negative, there we go. It's a max at theta is equal to pi over 4. Other thing to keep in mind with this problem is that if the one angle is pi over 4, the other one has to be pi over 4 as well. Now we were asked to get the perimeter. So the perimeter is equal to, if you go right back to the original, is 12 cos theta plus 12 sine theta plus 12. So all we do is substitute in our number. So the cosine of pi over 4 plus 12 times the sine of pi over 4 plus 12. So the perimeter is equal to 12 times root 2 over 2 plus 12 times root 2 over 2 plus 12. And the perimeter is going to be 6 root 2 plus 6 root 2 plus 12. So the perimeter is equal to 12 root 2 plus 12 centimeters. So the maximum perimeter is 12 root 12 plus 12 centimeters when the angles are pi over 4 and pi over 4. So that's it for this one. I'm going to do the other two questions later for the next, but this gives you a chance to work on some of these questions, keeping in mind that it is fairly transferable. You will see lots of variations of these problems, but they all do basically follow the same pattern. Thank you for your time.